Good afternoon. My name is Lawrence Mobes, and I am an editor here at Manufacturing Engineering Magazine. I'd like to firstly welcome everyone to another edition of the SME Media Webinars. We're glad you're here. Welcome. Our topic today is how laser beam shaping improves welding and metal additive manufacturing applications. Today's presentation is sponsored by Civan Lasers. Civan Lasers is a global leader in dynamic beam laser technology, revolutionizing the field of high-power laser applications. Their patented coherent beam combining and optical phased array technologies enable real-time control over beam shape, frequency, and focus, unlocking new possibilities in welding, additive manufacturing, and materials processing. Today's presentation is sponsored by Civan, as I mentioned, and our presenter today is Ami Spira. Ami Spira is the general manager of Civan Lasers USA, leading the company's North American operations and driving the adoption of dynamic beam laser technology across key industries. Before I turn things over to our presenter, I'd like to outline how the webinar today will proceed. On the right side of the screen, you'll see a question and answer box. If at any time during the presentation you'd like to ask a question, please type it in this box and send it along. These questions will be answered at the end of the presentation. Should you experience any difficulty or have any other questions during the webinar, such as a blank screen or a lack of sound, please use the Q&A box to alert us and we'll respond individually in writing with a suggested fix. Also, this presentation is being recorded and it will be available to view later today. You may then watch the recorded session of the webinar at a time and a place when you have a little more bandwidth. You may also watch the webinar as many times as you wish to catch details you might have missed the first time through or for any other reason. All you need to do is sign in again using the same credentials you used to join us just now. If you wish, you may share those credentials with colleagues who might benefit from learning more about this topic. Now, if everyone's ready, I'd like to turn the microphone over to Ami Spira. Ami, the stage is yours.
Thank you, Lawrence. And thank you everyone for joining this webinar. And in my webinar today, I will present dynamic beam shaping, which is one way or one technology to generate beam shapes in lasers, which is used in welding and additive manufacturing. And I will elaborate a bit more on our technology and the benefits that beam shaping give to these applications. So I will focus on the dynamic beam laser, which is the laser that we do at Civan Lasers. It's a fiber laser in a wavelength of 1064 nanometers. And what is unique about this laser is that in the focal plane, we are able to generate any arbitrary beam shape in very high details that allows us to achieve applications that are not possible in other beams. As I mentioned before, using the same laser, the same technology, we are able to use it for welding and additive manufacturing, also for laser bed fusion, and also for direct energy depositioning. Each application has its own benefits, but the fundamentals are very similar to each other. So the technology that we use for our laser is called coherent beam combining and optical phase array. And the idea behind it is that we start with a same laser source. So we start with a seed laser, which is a low power but high brightness laser source. We then optically amplify it and divide it into tens, or even in some cases, depending on the laser configuration, to hundreds of different channels. Each channel means that we have a fiber amplifier and an electro-optical phase modulator, which allows us to control the relative phase of the specific channel. We then take the fibers that come out of all these channels and we make an array out of them. And what happens is that when we emit the light in the far field, the different beams, they overlap. And because they are coherent to each other, because they are from the same laser source, they generate constructive and destructive interference. And with that, it generates a diffraction pattern that is unique to the different phases that we have. And by just changing the phases of the different channels, we can then influence the location of this diffraction pattern. And by that, we can steer the beam in very high frequencies just by electronics, by change of the phase. So just to illustrate that in a better way, you can see in the following movie, in just a second, this animation. So what you see here is basically by just changing the phase of the different channels, we can then change the location of this diffraction pattern. And with that, we can steer the beam in very high frequencies. And that is what allows us to generate different beam shapes. And just to show that again in more detail, close to real life. So this is the laser head we have. Out of this laser head, we have all the beams coming out collimated in parallel to each other. This is the array I mentioned before. And then after the focus lens, they all meet at the focal plane. And by a change of the phase, we then are able to steer the beam in the X, Y, and Z axis. And what you can, if you can imagine, this ability to steer the beam in the X, Y, and Z axis really is possible to break it down to the 4 features that you see here on the screen. So the first one is the beam shaping. This means that we can control the geometry of the beam shape that we are getting. The second is the shape frequency, meaning that we can control how fast we are generating this beam shape. Either we are doing it very slow in time to complete a cycle of a beam shape, or we are able to do it very fast. The third feature is the shape sequence, which means that because we are able to change between beam shapes so fast, we can then, in the same job, switch between several beam shapes and have a benefit of the different parameters or features that each beam shape has. And the same way we can steer the beam in the X and Y, we can steer it at the Z axis, which is what we call the focus steering, and that also has some benefits, which I will mention later. So I will present a couple of slides about each of these features and go more in depth. But before that, just when we are combining, when we combine all of these features together, really what it gives us is the ability to control the thermal aspect of either welding or additive application, and the dynamics of the molten material. And with that, we can control the length of the melt pool, we can control the geometry of the keyhole, we can tailor either the weld or the hedge that we receive in this process. And even what is more unique is we can influence the solidification process, and with that, everything that comes with that. So now just to go more in depth about each of the features I said earlier. So the first one is the beam shaping. So what you see here on the screen, this is the software that comes with the laser. This can be used either in the computer that you operate the laser with, or even you can use it offline, which allows you just to design different beam shapes. With this simple grid, you click and you design the geometry of the beam shape you have. You can see in the simulation in the window here on the right, what is exactly the power distribution that you're going to get at the focal plane. And with that, you can then upload it to the laser and use a new beam shape. And what you see here in the bottom are just a couple examples of different beam shapes that we generated with the software and used with our laser. Now, why is this important? What is unique about it? So in the following slide that you'll see in a minute, we are now trying to, we now are using a beam shape, which is a triangle beam shape. But the difference between what you see on the left and on the right is that on the left side, the orientation of the triangle is the left, and on the right, it's 180 degrees. And what we show here is on top is a simulation of the velocity of the melt flow in these two different beam shapes. And we can see how they differ from each other. What you see here in the middle, so this is an image, a top view of the weld, and you can see that they look different. And when you look at the bottom, it's a longitudinal cross-section. And you can see how the weld looks very different from each other. One has many transverse hot cracks, and the other has very few. And the idea is that just by controlling the power distribution, the beam shape you have in the process, you can influence what is happening inside the melt pool and the welding process. And this is true for many different materials and many different beam shapes. My next slide, what is showing is two high-speed video cameras that are Welding aluminum series 6. What you see on the top, this is a beam shape, the ring and the core, using a disc laser, which is another method for beam shaping. And what is on the bottom is a beam shape of a triangle. And I will play the movies again so you can see. But if you look carefully, you can see that the process is very different from each other. The cooling rates are very different. The geometry of the melt pool and the keyhole, the flow of the melt pool, you can see are very different. And then if you also, of course, look at the result, what you see here is the longitudinal cross-section. You see that in the top we have much more porosity and cracks in comparison to the bottom. And again, what we show is just that by optimizing the beam shape for the process, you can get a very different process. To the application, you can then get a very different process, and with that you have a much better control of what is happening. Also, which I find the most astonishing, is that by choosing different beam shapes, we are able to influence the microstructure. And what you see here, this is work done by Warwick University in the UK. They are showing different beam shapes that are used. So this is a thin aluminum, and you can see that also there is a different microstructure and also different mechanical strengths in the testing that they have done. So without saying what is a good beam shape, what is a bad beam shape, and of course that really depends on the application, this is just showing that with this tool, with beam shaping, you now can also influence the solidification process and hence also the microstructure. Another unique feature that is with the dynamic beam laser that does not exist in other beam shaping methods is that we are able to change the orientation of the beam shape on the fly. So what you see here, this is again, high-speed video camera of welding of this battery cooler, which you see in the bottom. And what we are showing in this video is that we are able to use a non-symmetric beam shape, in this specific case, a spiral beam shape, which gives us good results in this specific application. And if you can see in the movie that the orientation of the beam shape is changing as it's moving. So what is moving the beam shape, what is doing the large motion movement, is a galvo scanner. But within the melt pool, in the area of a couple of 100 microns, what is changing the orientation of the beam shape, that is by the phase control, or in other words, the technology in our laser. And what this does, it really opens a new opportunity for new beam shapes that were not possible with other lasers, because even if you are able to generate a beam shape, but you're not capable of changing its orientation, then what happens is the process changes every time you are changing the orientation of the beam shape. And with this laser, you can maintain the same orientation in all the different parts of the weld. So now I'll be talking about the second feature of the laser, which is the shape frequency. And in the shape frequency, really what we are showing is how we are able to generate a beam shape by jumping from one point to another. So what you see here, the movie that is playing now, we are currently generating a specific beam shape. And what you see now that is playing in the bottom picture, so we are actually generating a smiley beam shape. And what is actually happening is that if you look at the smiley beam shape, it's the average power distribution density that is happening while we are jumping from one point to another. And this is the key understanding of what the shape frequency is. And we can control this frequency, and that, as you will see in the following slides, also helps us to control and influence the process that we are working on. So here's one example. This is a longitudinal cross-section of a part of a aluminum die cast. And what you see on the top is we're using a beam shape with a frequency of 250 kilohertz in comparison to the bottom, which was a frequency of 500 kilohertz. And you can see how the parts are very different and the process is different. And just an example of how by even if you are using the same beam shape, but just using a different frequency, you can influence the process. Another example is welding of aluminum to copper. So you see here on the top, it's the aluminum, and the bottom is the copper. And what you see here in the blue is the concentration of the copper, and in the red is the concentration of the aluminum. And each column is a different frequency. So the left column is 100 kilohertz, the middle column is 200 kilohertz, and on the right we have 300 kilohertz. All are using this same beam shape of a spiral, same feed rate, same power. So basically the only parameter we changed here was the frequency of the beam shape, and you can see that how the intermetallic mix between the different frequencies is different. And again, this is just a tool that gives you more control over the process. What I show here is a slide, a work that was published by Fraunhofer IWS, which are in Dresden, and they did using the dynamic beam laser and intensive research on copper welding. So this is just one slide out of the lengthy work they did. And what I want to show here is that they tested many different beam shapes in many different frequencies for each of these set of shape and beam shape and shape frequency. They did the cross section, a top view of the weld, and also a cross section to see the quality of the weld. And then what they did is they generated this map where basically they defined the quality of the weld in these 4 different colors, and then taking all of the different beam shapes that they have tested in the different frequencies, they generated this map. And so what are the regimes or window parameters that gave them a good quality weld? And the idea of this, or what I'm trying to present here, is that even sometimes using a specific beam shape, you can see that just by changing the frequency of the beam shape, like you see here, in some areas, some windows of frequency, we would have a bad weld, and in others, we would have a good weld. And this really is a very powerful feature that can give you more control over the different process and what you are trying to achieve. And just to maybe emphasize this point a bit more, so this is a work done by University of Stuttgart, again, using the dynamic beam laser and copper welding. And they really also got to a very similar results. And what you can see here is that using the same beam shape, but just changing the frequency of the beam shape again, we have a very different process. And it's just very interesting. And I won't go in depth now to explain why this is happening, but there is a very nice physical explanation also that why in certain frequencies, even when we are using the same beam shape, we end up with a bad weld. And when we either move higher or low in the frequency, then we have a very good zone that we have high quality welds. So after talking about the second feature, which was the shape frequency, I'll move to the third feature, the shape sequence. And the idea behind this is that each beam shape has its own characters and benefits. So maybe I'll use this first one as a simple example. So in general, if we use this single point, that means that we concentrate a lot of the energy or most of the energy in a very tiny spot, which in most cases leads to a very large penetration. But the downside of that is that there is a very small keyhole. And that means that every small fluctuation leads to collapse of the keyhole, which then leads to porosity. On the other hand, if we use this very wide beam shape, then we are able to maintain a very large keyhole. But the downside of that is that we have a little penetration. So the idea behind this shape sequence is trying to combine both of the beam shapes and enjoy the benefits of the two. And just to explain that a bit more, so what you see here in this example is what happens when we use a single point beam shape. So we have very large penetration, but we have, as I mentioned, a very narrow keyhole. And this also leads to very bad flow and to the fluctuations that if you look at the end of the welding process, that means that in most of these cases, we would end up with this root crack. But when we combine both of these beam shapes, what we call the shape sequence, so we are enjoying the benefit of this single point beam shape. But after 5 milliseconds, we change to this wider beam shape, what we call this U beam shape, which gives us a much wider opening of the keyhole. That means less fluctuations and a more stable process. And the end result of this shape sequence is that we then get a weld without this root crack. And as I presented before, so there are many different sequences that could be used in many different applications, but this really opens even a wider toolkit of how you can combine several beam shapes. It could be even more than 2 beam shapes. It could be actually up to almost 30 beam shapes in one process. And there's just many, many interesting applications of where this can come in hand. Just to give you one more example for this is welding of hairpins. So this is a very common application in the e-mobility industry. So the stator of the electric vehicle motor basically has hundreds of these hairpins that need to be welded together. And it's enough that one of these connections is bad, the entire part will not work and needs to be either go through rework or be or basically go to the garbage. And there are many strategies today of how to weld this part. And the common to all of them is that it's some kind of a wobble weld. So that means that you take a single point and then you wobble it between the 2 hairpins in different motions. But what happens is that whenever you cross this gap between these 2 pins, it usually leads to spatter and porosity. And with this shape sequence, we were able to overcome it by starting with this 4-point beam shape. Afterwards, after 5 milliseconds, switching to this large Gaussian beam. And with that, we were able to eliminate the spatter and the porosity, get a high quality weld. And also another benefit that we have from this process is it was a much shorter process, with much less heat input, which has specific benefits in this application. So I hope this gave you an idea of different case studies that the shape sequence can come in hand. I do want to also take just 2 slides to talk about the focus steering. So the dynamic beam laser has the features of a single mode laser, which means that it's a high beam quality, which means that we have a very low divergence. And because we have a very low divergence, we have a very large depth of focus, as you can see here. So just to give you an idea of what that means, large depth of focus. So you can see here that the depth of focus is dependent on the focal length that we use. And here are different focal lengths and the different depth of focus that we can achieve for each focal length. But in addition to that, we can also steer the beam electro-optically. So as I mentioned earlier, we can move the Z-axis in addition. And you can see here the capability to move the Z-axis in relationship to the focal length we use. So the bottom line of this is that we can reach very large depth of focus, which can give us several benefits, either in welding of very thick sections, so we can get a uniform power distribution in all of the wall of the part that we are welding, but also other interesting applications which are also very relevant for additive manufacturing, for example, is when using a galvo scanner, we are able to compensate on the movement of the Z-axis electro-optically by the use of focus steering. So that means that we do not need to use a f-theta lens or a mechanical movement of the focusing lens to reach this compensation, which makes it either much cheaper when we don't use the f-theta lens, or it gives us even a much larger scanning field, and faster when we don't use a motor to use the focusing lens. So now I will give a couple of examples, first in welding, afterwards in additive manufacturing, of the benefits of the dynamic beam laser and the beam shaping in real-world applications. So in first, I just want to talk about laser welding and why beam shaping is necessary. So laser welding, even though it's existed already for several decades, it's a relatively new joining technology in the market. There are many other technologies that exist, that in fact are most of the market. But lasers have some unique features. The ability to concentrate a lot of energy in a very, very small spot and move it in high feed rate gives us the ability to bring in a lot of energy to the material with very little heat going to the sides. And what that allows us to do is really to have a much faster weld, with much little heat input in the process, and is a faster and more efficient process. But the issue with that is that it's very challenging and not possible for all of the different applications. So just to give an example, when we try to apply laser welding in, for example, thick welding of thick sections, we can find very common defects such as the root cracking or porosity. And most of the lasers are challenged to solve this. But as I will show you soon, when we are starting to apply these beam shaping methods, we are able to solve and overcome many of these challenges. And just to give one example of where this comes in hand and what are the benefits of the lasers. So what we are doing here is comparing two common methods today. So the first is arc welding. It could be either MIG welding or submerged arc. But in all of these cases, we will have to do a multi-pass process because we have a very low penetration. So we have to fill the bevel each time with a little filling material, wire or flux. And what this leads is to a high heat input, which leads to a large heat affected zone, which also leads to a lot of distortion. But when we use the laser, we are just doing a single pass, which is a very fast with very little heat input. So it allows us to really reach a process that is just one pass with no need to do any beveling ahead of time. And also what is very interesting and unique is because we are welding basically with straight walls, we are eliminating the need for any filler wire, and we are just using an autogenous process. And I'll just show now a couple examples of welding applications that we were able to achieve using these different beam shapes. So if you see here, this is a single pass weld of aluminum in the depth of 9 millimeters. You can see the cross section of the weld. The next is welding of 1 inch of a mild steel material. So what you see here is the root weld of the laser, and then within the same pass, just using one pass with filler wire to cover the undercut that occurs due to the unperfect fit of the two plates. Here is an example of welding of stainless steel. So this is a 30 millimeters thick in a single pass. And just to compare that, if this is a process we would want to do with using TIG, for example, this would require anywhere between 10 to 15 passes with the need to flip the part to manage the distortion. And if we are, to our specific application, capable of doing a double side weld, then we can reach even thicker parts. So what you see here, this is a double pass weld using 24 kilowatts, reaching 45 millimeter penetration. And this is a 60 millimeter double side weld using approximately 60 kilowatts. Now I want to talk about copper applications, so very common in the automotive industry, but also in many other areas. And the challenges that we face when we weld in copper is the high thermal conductivity of this material, which leads to inconsistent welds, a lot of porosity from the fluctuations that are in the process, and a lot of spatter as well. And what we focus in when welding copper is going on the more challenging applications. So either welding of very thick copper. So what you see here is a overlap of 4.6 millimeters and 4.6 with a penetration of almost 8.2 millimeters. You can see with no porosity. Welding of hairpins, I mentioned this earlier. And also when we sort of weld asymmetric copper parts, so it could be either cables to just a thick part of copper or otherwise. And by using these different beam shapes, we are able to find the optimal parameters and get a high quality weld. Next applications I would like to explain and show some results is welding of die-cast material. So the challenge in die-cast is that in the casting process, we have hydrogen that is captured in the base material. And then when we warm up the material, they expand and they are then stuck in the material, generating this, causing to this porosity. But what we do is we use this spiral beam shape, which then steers the beam and forces the hydrogen to rise up to the surface and evaporate. And in addition, what we see is that also this spiral beam shapes gives us a much more elongated melt pool that gives more time for the porosity to rise up to the surface and then evaporate. And when using this method, we then were able to weld die-cast material. So what you see here in both of these examples are just die-cast, different high-pressure vacuum die-cast, aluminum die-cast with less than 3% porosity. In both of these applications, it was a leak-tight part that was needed to be welded. And also we did some testing for welding of die-cast with other materials, so either die-cast with aluminum series 3 or even die-cast with extruded aluminum. And coming close to an end, I also want to talk about using beam shaping in additive manufacturing. So to see here, this is a work that was published just a couple of months ago by a Friedrich Alexander University based in Germany. And they did some work using dynamic beam shaping for direct energy depositioning. And what you see here is a average frame of a much larger video. And if you look carefully, you can see that the geometry of the keyhole that is shown here is very similar to the beam shape that you can see on top. So just showing that what we are really able to influence the geometry of the keyhole by using different beam shapes. And then if we look here, so this is a longitudinal cross-section of a hatch, and you can see that they have put the beam shape used. So they did a sequence of beam shapes through this one hatch, and they more or less positioned the beam shape in the location according to time of where it's supposed to be. And you can see difference in the penetration depth of this hatch by switching between beam shapes. But also, they were using a pyrometer to measure the temperature within the keyhole and melt pool area. And what is interesting, even though in all of these beam shapes we were using the same power level, the temperature, because of the distribution of the energy within this beam shape, varies and is different. And then just to put it all together, really, is that we can see that all of this also influences the microstructure we have in the different locations according to the beam shape. And I think this is a very beautiful work that they did, showing how by using different beam shapes, you're really able to influence the process here and into even the level of the microstructure. And as I mentioned, also this beam shaping can be used for laser powered red fusion. So to be honest, there was not as much work as done in this area as we had in welding and direct energy depositioning. But some initial work shows us very similar stuff that we were expecting to receive. So first, by changing the different beam shapes, we are able to influence the geometry of the hatch, which means that we can easily change in the same laser power while we are moving the size of the beam shape, and then we can have either a more detailed hatch or a larger one. And also the same things that we can see in welding. By using these beam shapes, we are able to influence the material properties, which means either the intermetallic mix or in some cases of materials that are keen to hot cracking. We're very sure that these same concepts of beam shaping can solve them as well. And with that, I'm coming to an end. So I just want to invite the viewers and the participants. We have 2 demonstration labs in the US. One is located in Idaho, the second in Michigan area. And if this technology is interesting for you when you're interested either to test a specific application or just to see this laser operating, you're welcome to contact us, and I'd be very happy to host you in one of these labs. And with this, I am open for questions.
All right, well, thank you very much, Ami. As Ami mentioned, that concludes the formal part of the presentation, but we did receive some questions in the chat during the course of the presentation, and we can address some of those now. So if you're unable to stick around to the end for members of the audience, feel free to revisit the webinar anytime you want, and it'll be available. You can revisit it anytime you wish.
I'm gonna go through some of the questions I see in the chat box. So I'll just read out loud. The first question I see. So the question is, what is the threshold in terms of material thickness when laser welding become non-applicable? So I hope I was able to answer that in the slides that I've shown. I've shown up to 60 millimeters. We also did some trials using a very high power laser of 100 kilowatt, and we were able to demonstrate a single pass weld of up to 73 millimeters, so almost 3 inches in a single pass. However, this process is not a stable process yet. It's not certified. It's very hard also to keep researching that because it requires a very high power laser, but it just shows the capability. And really, if you are able to weld a single pass weld of 3 inch, if you use the same power level for 3 inch, maybe this could even lead to welding of 120, 140 millimeters using a laser. The next question I see here is, do you provide the laser or a turnkey solution? So we provide the laser source, and we have partners worldwide, also here in the US, system integrators. So both of these companies, that's what they do. And together with them, we are able to offer a turnkey solution to our customers according to their needs. The next question I see is, what are the laser possible power levels? Our lasers, our dynamic beam laser lowest power level starts from a 7 kilowatt. It is a tunable, so it could even operate in levels of tens of watts. And it goes up to 130 kilowatt model. So the common steps we have, so these are off-the-shelf products, is 7, 14, 28, 42, and 130 kilowatts. The next question is, how do you decide which beam shapes and other parameters to use for each process? So this is a very interesting question, and I guess it's a more complicated answer, but I will try to simplify it. So there are several ways to how to get started. The first and the most easiest, we already developed a quite extended library of parameters for different materials from the different projects we worked up until now. So we provide this recipe book and the support of how to get started. Later on, I think after using this laser, we see that really it's very intuitive. So when working in a specific application, you can understand what are the challenges behind this application. You can come up with a theory about how a beam shape can solve it. And because it's so easy and fast to generate a new beam shape, with just a short trial and error, we see that it's very easy to find new beam shapes and parameters that way. And last, we started to see work. It's still in academy. This is not used, but a combining of simulations and AI models. So there's some very interesting work showing how by defining what is the geometry of the keyhole that you want to achieve, what is the influence of that on the welding process, And the second you know what the geometry of the keyhole is, you can then try to achieve that with different beam shapes that our laser can offer. So I hope that answered that question. And I see the last question here is, have you attempted to weld other materials such as ductile iron or with this method, ductile iron? So specifically ductile iron we did not attempt, but really we have very wide range of applications that either us or customers have used already. Steels, copper, aluminum, titanium, dissimilar materials, and much more. And also in the additive, our customers are already using some very interesting alloys. So I guess the answer to that is yes, but I guess the best way to get an answer for your specific material is to reach out, and I can see what I can, with which information I can provide you with.
All right. Well, thank you very much.
Thank you everyone for participating and for sending your questions. Wish you all a great day.
All right. Thank you very much, Ami. We certainly appreciate your webinar today. And as today's webinar has shown, dynamic beam shaping unlocks new possibilities in welding and metal additive manufacturing, pushing the boundaries of what's achievable and enabling advanced applications previously out of reach. We definitely appreciate the information you share. I'd like to thank our presenter, Ami Spira, and of course the whole team at Civan Lasers. If you're interested in getting more information, you may contact them directly at www.civanlasers.com. And remember that SME and SM Media can help you keep abreast of all the latest developments in advanced manufacturing systems and really just about anything that has an effect on the world of manufacturing. You may check out our podcast at advancedmanufacturingnow.com to listen to a wide variety of manufacturing professionals discuss the challenges, opportunities, and factors impacting manufacturing today. And don't forget to keep an eye out for breaking news and coverage of the latest technology and strategies for manufacturing at advancedmanufacturing.org. Thank you all for joining us on this SME Media webinar. We hope you found it useful and informative, and we hope that you will come back and join us for future webinars. Thank you.